Have you ever wondered about how entanglement really works? What does it really mean when you say an object is in a superposition of two states? What does it mean for an electron to be in place A and place B but nowhere in between? What is quantum tunneling? To answer all of these questions, we're going to be starting the quantum computing series here at Bari Science Lab. Welcome to the first lecture, in which we're going to dive into postulate number 1 of quantum mechanics, and that is the postulate of superposition. Let's get started with the double slit experiment. Now, the double slit experiment goes like this. We have, a double slit and coherent light, meaning light that is coming in with a steady stream, not light from a light bulb, which is very disorganized, random, but light from something like a laser, a monochromatic laser that might be shining blue light or red light or green light. So you've got light that's coming in, this is coherent light, coming in, all of them have the same phase, right? And so the light is coming in. Maybe you don't see it if I do that, so I'll just draw it like this. Okay, so these are the planar light waves coming in, and as soon as they hit the double slit, what are they going to do? They're going to act almost like a wire coming out of a slit. So they're going to diffract, right? So these waves are going to diffract, and the narrower the slits, the more circular the diffraction. So you're going to end up with something like this, where you've got spots with constructive interference and spots with destructive interference. And so on the back wall, what do you observe? On the back wall, what do you see are some very bright peaks, some dark spots where there's no interference at all, or there's destructive interference, and after the dark spots you see bright spots again, but these are a little less bright, right? These are a little less bright. And another dark spot, and this one is another bright spot, but this one is even less bright. Another dark spot, another bright spot, this one is even less bright. So what do you see? You see a peak of brightness right here, where most of the electrons are going to end up, and then a smaller peak here, and a smaller peak here, and so on and so forth. And you repeat for the other side. And so this is going to be the interference pattern you observe on the back slit. This right here is the interference pattern on the back slit. And what does this interference pattern tell you? It tells you that there's going to be a high probability of finding electrons or photons over here, and a lower probability of finding them here, a lower probability of finding them here, so on and so forth. Now, let's talk a little bit about how we can analyze this double slit experiment. If you have two coherent light sources coming out of this double slit, so imagine that. Now, assuming that this is a spot of constructive interference, what can we say? We can say that this light wave clearly travels a shorter distance than this light ray, right? This light ray, you can just look at it and see that it travels a little bit more. And if you don't see that, think about a light wave that's really far away. Clearly this one travels more than this one, right? So how much more does it travel? Well, we can drop this perpendicular and find out. Let's call the distance between the two slits a distance d. And let's say, since that's constructive interference, this right here, this extra distance traveled by the second light ray has to be some multiple k of the wavelength of the wave, right? So if this was not a multiple of the wavelength, then you would not have constructive interference there. Instead, you'd have destructive interference, or not fully constructive interference. So let's call this angle right here theta. So the relationship we can state is as follows: sine of theta is equal to opposite over hypotenuse, k lambda over d. So d sine theta equals k lambda. We can use the small angle approximation to say that d theta is equal to k lambda. And from this experiment, you can find what the wavelength of light is. You can say light is what? D theta over k. And in fact, this is one of the easiest ways to determine the wavelength of red light, or any light for that matter. Using this simple experiment, you can determine how long one wavelength of red light or green light or blue light actually is. So that's how powerful the double slit experiment is. Now, that's the fundamentals of double slit experiment. What does it teach us about quantum mechanics? That's what we're going to find out when we take the double slit experiment from John Young's version to the quantum version. And what is that quantum version? The quantum version occurs when you have the following: of shooting monochromatic light at the double slits. What if we shot one photon at a time? Instead of firing a steady stream of photons, let's say I have my double slit again, but now I'm going to shoot only one photon at a time. So here's one photon. Okay, here's the back slit again. I'm going to erase the interference pattern for the steady stream of light, and we're going to just replace it with the back wall. Let's see what the interference pattern looks like for just one photon at a time. Now, one photon at a time, there's no way it can act like a wave, right? This photon has to either go through this slit or through this slit. It can't go through both slits, right? Well, after we shoot one photon and another photon and another photon and wait for all the photons to pile up, what do we see? We see this interference pattern. That's right, it's the exact same interference pattern. Even when you shoot one photon at a time, you still get a wave-like interference pattern. And that is spooky. That is spooky interference pattern. That means that this photon, I mean, what is it interfering with? When we had waves, they interfered with each other and created spots. They created a zebra pattern where you had constructive and destructive interference. What is this photon interfering with? There's not another photon that it can, like, constructively or destructively interfere with. There's just one photon. And so the idea that physicists came up with is crazy when you think of it. The idea is that the photon doesn't choose which slit to go through, because if it did choose to go through one of the slits, you'd have a whole bunch of photons here, a whole bunch of photons here, and the rest would be basically dark spots. But that's not what we see. We see a wave-like pattern. That means that, and this is not a logical conclusion, let me make that clear, this is in no way obvious, but the idea that physicists came up with is that the photon goes through both slits at the same time. And that is the idea of superposition. Okay, and that is the fundamental postulate of quantum mechanics that we're exploring today, superposition. The photon goes not through slit A, not through slit B, but both slits simultaneously. That is completely wild if you think about it. It's like the photon shreds itself apart, goes through both slits, and then comes together and constructively interferes to give you this crazy wave-like interference pattern. Now that we know the basic idea behind the basic principle that the double slit experiment gives us, which is the principle of superposition, we can mathematically formulate it. And that's what we're going to check out next. Okay, great. So now we're going to be talking about the next level, and that is the Mach-Zender interferometer. That's going to let us investigate superposition at a deeper level. So let me draw it out for you. What we have is the following situation. We have a gun. Now, this is not a gun that shoots bullets, it's a gun that shoots photons. And it's going to be shooting those photons like that at a beam splitter. What is a beam splitter, you ask? A beam splitter is nothing more than a box that splits a light ray into two separate directions that are perpendicular to each other. So for example, a beam splitter is going to take this ray of light and let half of it go through, half of it it's going to reflect. That's it. That's all a beam splitter does. So perfect 50-50 beam splitter sends 50% of the photons up, 50% of the photons down, and then some of the photons that have been reflected, have been allowed to pass through the beam splitter. Those 50% of photons are going to be reflected from this wall, and the 50% of photons that were reflected by the beam splitter, they're also going to be reflected here, and they're going to enter another beam splitter. Okay, here's another beam splitter, and this beam splitter is going to be just so that it recombines these two light rays, and they're going to be recombined and enter this detector. I'm going to call that D0, and then there's another detector here, but of course there's no light rays entering this lonely detector right here. Let's call that D1. Okay, the name of this experiment is the Mach Zender Interferometer. Okay. So, why are we doing this? Why are we learning about the Mach Zender Interferometer? It lets us see superposition on a deeper level. So let's see what I mean. Let's say all the photons that are on the bottom, and what I mean by bottom is below the beam splitters, let's say they're in a state of 0. Okay? 0 we're going to colloquially mean to be the bottom. And the photons that are above the beam splitters, we'll say they're in a state of 1, which means top. Okay? This is by no means a hard and fast rule. It's just, I'm giving some labels to these states, as you do. Now, at this point, what is the state of the photon? Well, clearly it's in the bottom of the beam splitter, right? It's below the beam splitter. So we can say that its state is going to be in the 0 state. So we say it's going to be in the 0 state. Okay, that's the state of the photon. It's in the 0 state. In fact, let me put a 1 here. We're going to analyze the state of the photon here. We're going to analyze the state of the photon here after it passes through the beam splitter, here after it gets reflected, and here after it passes through another beam splitter. Let us begin. At the first, over here, what is the state of the photon? Well, clearly the photon is at the bottom, below the beam splitters, so we say that its state, ket psi, is 0. And don't worry, I'll explain what all this weird notation means in a second. We'll get to that, but for now, all we are saying over here is that the photon is below the beam splitter, its state is 0, because 0 is the bottom state, right? 2, what is the state of the photon after the beam splitter? Well, half of the photons are in the top state. Half of the photons are in the bottom state, and half of the photons are in the top state. Okay, so we say that the photon is in a superposition of the top and bottom state, and that's how we write this particular superposition. I'll explain where all of these come from in a second. Where this 1/√2 comes from, what does this weird symbol mean, why is there this kind of arrow or straight line here, why is there a bracket sign here. This probably looks very mysterious to you right now, but we'll get through it in just a second. For now, all you need to know from this is this equation, all it's saying is that the photon is in a superposition of the bottom state and the top state. That's all you need to know for now. We'll understand where this 1/√2 comes from, what this bracket, what this line represents. We'll get through all of that. But for now, this just means the photon is in a superposition of the bottom and the top states. And then at 3, what is the state of the photon at 3? Well, at 3, nothing much happens, right? The photon is simply reflected. So its state is actually going to be the same as it was in 2. 1/√2 0 plus 1/√2 1. And at 4, what is the state of the photon? Well, this time the state of the photon is going to be what? Well, the photon is back to the bottom state. So it's the state of the photon is simply going to be 0 again. So the photon first starts off in the bottom state, then gets into a superposition of the bottom and the top states because of the beam splitter, and then the photon stays the same in the third stage, and then on the fourth stage, the beam splitter recombines the top and bottom light rays and forces the photon to be back in the 0 state, in the bottom state. Now, let's take a deeper look at what all of this means. What does this line mean? What does this bracket mean? Why is there a 1/√2 in front of these bottom and top states? What does the number inside of the line and the bracket mean? What does all of this mean? All right, we're going to get to it right now. All of this notation is called Dirac notation. Okay, so we've talked about the double slit experiment, the Mach-Zender interferometer. Now we're going to be talking about Dirac notation, invented by none other than the famous Paul Dirac, Nobel laureate. Now, Dirac notation might seem very complicated at first, and it will take some getting used to. But after you learn the language, it'll be so much better than vector notation, which is the alternative. Dirac notation is the language of quantum mechanics. It's the language of the small world. If you want to know how things interact, how matter works at the small scale, you need to know Dirac notation. Well, you don't need to know. You'll suffer a lot if you don't know, but it's better to know. So, without further ado, let us learn Dirac notation, also known as bracket notation. It starts off like this. You have bras and you have kets, and you combine them to create a bracket. And a bracket is a scalar, a number. Let me show you what I mean. Here is what a bra looks like. Okay, so you would say this is bra psi. Nobody actually says that, but to get used to it, you can say this is bra psi. And this is what a ket looks like. This is ket phi or ket phi. All these Greek letters mean these are just different quantum states, just like ket 0 and ket 1. Remember, we said this was the bottom state in the Mach-Zender interferometer, and we said that this was the top state in the Mach-Zender interferometer. Well, you can say this is ket 0 and this is ket 1. Okay, this is bra psi and this is ket phi. Okay, and when a bra and ket meet together, what do they form? They form a bracket, which is none other than a scalar, a number. Now, let's take a look at an example. Let's say, okay, maybe I should not erase this so you have this in your mind. Let's say I have something like this. We have the state 0, this is bra 0, and this is ket 1. Okay, and when they come together, what is it going to give you? Well, in quantum mechanics, the great thing is that more often than not, almost always, two quantum states will be orthogonal, meaning they will be perpendicular. So bracket 0 and 1 is going to be 0. Bracket 1 and 1 is going to be 1, because not only are quantum states orthogonal, they're normal, they're normalized, so they're orthonormal. So this is orthogonal and this is normalized, and so that's why you say that quantum states are always orthonormal, which is the best case scenario for doing quantum mechanics. Great. So we know what bras are, what kets are. When they combine, they produce a bracket, aka a scalar, or otherwise just a number. Now let's talk a bit about probability. Okay, probability is a big deal in quantum mechanics because you no longer have a deterministic universe, you have a probabilistic universe. And when you have something like this, let's say you have I don't know, 1/√2 0 plus 1/√2 1, Remember, we saw this state coming out from the Zender interferometer. After the light ray had gone through one beam splitter, after the light ray went through one beam splitter, it was in a superposition of the 1 state and the 0 state. So some of the photons were in the bottom, some of them were at the top, and this is how you express their superposition. So this is a superposition of the 0 and 1 states. Okay. Now, with that being said, what does that mean? If I go into the laboratory and I take out my photon detector, how often will I detect the photons on the top state? How often will I detect the photons at the bottom state? To answer that question, we need a hero. And that hero is none other than Max Born, who realized that the coefficients of quantum states are none other than their probabilities. And that's why we have Born's rule. Born's rule says the probability of finding the photon at the bottom is the amplitude of 1 over root 2 squared, which is just 1/2. That means there's a 50% chance, which makes sense because this is a 50-50 beam splitter, sending half of the photons to the bottom, half to the top. This 50-50 beam splitter makes it such that if you take out your detector, if you take out your photon detector, you're going to find that half of the time you find the photons in the bottom state. And let's do the same for the top state. What's the probability? Well, it's the amplitude of 1 over root 2. Okay, which is just 1/2, right? So there's a half chance of finding the photon here on the bottom and a half chance of finding it here at the top. Okay, and that should make sense, right? Because half the 50-50 beam splitter sends half the photons on their way at the top, half of them on their way at the bottom, and so that's how you get this. Now you might be wondering, hey Refath, why are we doing amplitude of 1 over root 2? Why can't we just square it? Well, it's because in quantum mechanics we deal with complex numbers. So you could have a quantum state such as, let's say you have something like I over root 2, okay, times the 0 state, plus minus I over root 2 times the 1 state. Then the probability of finding the state in the 0, of finding the system in the 0 state would be what? It would be the amplitude of I over root 2 squared. And how would you find that? Well, you would take I over root 2 and multiply it by its complex conjugate, which just means negating the I. Okay? That would be minus I squared over 2, which is just 1/2 again. And you could do the same thing with the top state. That would be minus I over root 2 magnitude squared. This would be minus I over root 2, but now its complex conjugate would be plus I over root 2, giving you minus I squared over 2, which is 1/2. Okay, so if that was a lot of math, just go ahead, rewind, and watch it again. If you have any questions, I'm always happy to answer them down below. So that's how we express superposition, right? Superposition generally, we just looked at this example of the light beam entering the beam splitter and being cut in half. Half of the time you'll find it in the 0 state, and half of the time you'll find it in the 1 state. But now let's take a look at a generalized example. Now we took a look at a specific example. Now let's generalize it. A superposition of two states can generally be expressed as follows. You have two states, let's say it's the bottom state and the top state, and you have some amount of each state. That's it. That's all superposition looks like mathematically. This is superposition. This tells you you have a quantum system that is in the superposition of the bottom and the top state. This 0 and 1 can have different meanings based on the type of experiment you're doing. If you're doing a polarizer experiment, if you don't know what a polarizer is, it's just a kind of filter that filters the kind of light that's coming in. If you're doing a polarizer experiment, this 0 could mean a certain angle of the polarizer. If you're doing a Mach-Zender experiment, this 0 could mean the photon is at the bottom below the beam splitters. If you're doing a double slit experiment, this 0 could mean the photon is going through the bottom slit. It depends on the experiment you're doing, but just to give you an intuition for what these formulas look like, you can keep in the back of your head, okay, 0 means I'm at the bottom of the Mach Zender, 1 means I'm at the top. You don't have to keep that in mind, but it might give you something to hold on to, something to grip onto if you're getting confused about what this means. So all this means is that my photon is in some linear combination of the bottom state and the top state. So it's in a superposition. Okay? And the probability of finding my photon in the 0 state is none other than the amplitude of that coefficient squared, and likewise for finding it in the top state, the amplitude of beta squared. And what's that going to be? Well, if alpha, let's say this alpha right here is A plus BI, and this beta here is C plus DI, since they're both complex numbers, then their amplitude squared would be none other than A plus BI times A minus BI, right? Because this is A alpha and this is alpha conjugate. This is the complex conjugate. Okay, and you can figure out what that is. This is simply going to be A squared plus B squared, which is none other than the Pythagorean theorem. Likewise, you can do the same thing here. The reason why this is plus B squared and not minus is because you have BI minus BI, which is minus BI squared. I squared is minus 1, so you have plus B squared. Likewise, for this one here, you have C minus DI, gives you C squared plus D squared. So all this is really doing right here, all this probability amplitude is really doing, is it's doing the Pythagorean theorem in quantum mechanics, right? So this is none other than your old friend, the Pythagorean theorem. Okay? So now that we've kind of understood the language of quantum mechanics better, we know what superposition is, we know how to find probability amplitudes, we know how to find the probability of finding the quantum system in this state, of finding it in this state. Now we can understand the Mach Zender interferometer experiment even better. So let's do that. So here we are. Okay, let's do the Mach Zender interferometer experiment, but this time with the real math. So, first, the light beam is going through. Let's say the beam splitters are right here. So anything below the beam splitters is the 0 state. Anything above is the 1 state. Okay, we're good to go. Let's get started. In the beginning, the photon is clearly in the bottom state. So we say over here that the photon is simply in the bottom state. Hopefully that's clear. If it's not, leave a comment down below. The photon is in the bottom state. Okay, now there's a beam splitter. A beam splitter that's going to take this photon, slice and dice. Half of it goes up, half of it goes down, and now the photon is in state 2. And state 2 is where the math comes in. Now we know the language of superposition. We can express this beam splitter mathematically as something known as the Hadamard. The Hadamard, you don't need to know what it is. It's just like a function. It takes some kind of a quantum state in, spits out some kind of a quantum state out. So we're going to apply the Hadamard to 0. Okay? And what does the Hadamard do? The Hadamard is written as where h is equal to, the Hadamard is written as 1 over root 2 of the 0 state, of the 0 state, plus 1 over root 2 of the 1 state. Okay, that's what the Hadamard operator does. Let's apply it to this 0 state. So let's see what we get. Okay, so, let's write it nicely. The Hadamard operator applied to 0 gives you over root 2, which you might be, more accustomed to seeing as, right? This is what we saw just in the previous example. The probability, my chalk is not here anymore. The probability of finding this quantum system in the 0 state is simply the square of 1 over root 2, which is a half, and the probability of finding it in the one state is simply the square of the probability amplitude, which is a half, right? We saw that just a few seconds ago or minutes ago. Now, the light rays are going to be reflected off these walls and enter a second beam splitter right here. And I want to know what is the state of the light beam after it passes through the second beam splitter. We know that we should end up with 0, right? Because it ends up in the bottom state clearly. But is that what the math gives us? Let's see. So this is the third state. You might have noticed I ignored the state where after it reflects, because that's just a phase change and a global one in that, so it doesn't really matter. So the third state, what is the state of the photon at the third state, at the third stage? So at the third stage, we apply the Hadamard operator again to the 0 state, right? You apply the Hadamard once for this beam splitter, another time for this beam splitter. So what do you get? Well, this is the same as HH0. Recall that, or not recall because I haven't said it yet, but the Hadamard, and indeed almost every quantum operator, including the Hadamard, is a linear operator. Linear operator. What that means is that when you apply a linear operator, let me explain what a linear operator is here. When you apply a linear operator to an addition, it's the same. If you apply a linear operator to a sum, it's the same as the sum of applying the linear operator to each addend. And likewise, if you apply a linear operator to some scalar times the state, it's the same as taking that scalar and applying the linear operator to that state. So C times f of a, where f is the linear operator in question. So now let's apply that idea of linearity. Okay, great. I can't pronounce. So let's apply the idea of linearity, great, to quantum mechanics and the Hadamard. So we're going to have h, but now we already know what h applied to the 0 state is. It's going to be 0 plus 1 over root 2, which is the same as this. And now we're in business. Let's go ahead and apply the Hadamard operator to both the 0 and 1 state. So we're going to have h0 plus h1 over root 2. Now, what is h0 going to give? h0 means that you're going from the top, or you're going from the bottom. Hadamard splits you into a superposition of the top and bottom. This is going to be something known as the plus state, and this right here is going to be something known as the minus state over root 2. Now you ask, completely justifiably, what is the plus state? What is the minus state? Simple answer. Well, not so simple, but here it is. The plus state is nothing more than a superposition of the 0 and 1 state, right? We've seen that over here. And the minus state is the exact same as the plus state, but there's a minus sign, which is why it's called a minus state. So when you add these two guys up, what do you get? The 0 state plus the minus state. Add these two, you're going to get 2. You're going to get 2 times the 0 state over root 2. Right? And so we can plug that back in here, and let's go ahead plug it in on the top. So we'll have 2 times the 0 state over root 2 times this root 2 gives us 2 on the bottom. So we're left with a final state of 0 as expected. That is the math behind the Mach Zender interferometer. Folks, thank you for watching the first episode of Quantum Computing. In this lecture, we talked about the double slit experiment, the Mach Zender interferometer, Boses Rule, the math of probability amplitudes, the postulate of superposition, and a lot more. We talked about Dirac notation, brackets, how brackets combine to produce a scalar, and all that cool quantum mechanical stuff. In the next episode, we're going to be diving deeper into Boses Rule and probability amplitudes, so stay tuned, and if you have any questions or comments, leave them down in the box below. I'll see you in the next one.